Our bell ringer question today is, balance the following equation. C2H6 gas plus O2 gas yields H2O gas plus CO2 gas. Hopefully you paused the video, took a moment to write that down, and hopefully you have this. 2C2H6 gas plus 7O2 gas yields 6H2O gas plus 4CO2 gas. So it might be tempting in a reaction like this to try to divide everything by 2 because we've got 2, 6, and 4. It might be tempting to try to simplify this. However, when we do that, because 7 is an odd number, we will end up with a fractional coefficient, and this is not possible. The only time we use fractional coefficients is if we are balancing equations or reaction steps in order to calculate the overall enthalpy of the overall standard heat of formation. That is the only time we're going to use fractional coefficients. Otherwise, when you're balancing any old regular equation, you have to use whole integers. So, a good reminder. Today, we're going to be talking about reaction direction and predicting reaction direction. Our learning objective is I can compare K and Q to determine the direction a reaction will proceed from a given point. So we've laid a lot of groundwork for Q and K, and today we're kind of going to get into some of the beginnings of the mathematical calculations to describe how a reaction is going to behave when we are given, in this instance, K. So we're given the equilibrium constant, and then we're also going to be given some of the concentrations for Q. So we're going to be able to actually calculate a Q value. And when we compare Q and K, what we're able to see is that allows us to predict or determine how a reaction is going to proceed. This obviously is dependent on us understanding the relative size of Q. So if you think back to what Q is the ratio of products to reactants. If we have more products, that means that we are taking a larger number and dividing it by a smaller number. Relatively, that will give us a larger Q. If we have a smaller number of products and a larger number of reactants, we are going to then take the smaller number divided by a larger number, and that will give us, relatively speaking, a smaller Q value. So, what does this look like for us to actually compare Q and K? Let's take a look. So, first off, the basis of all of this is the understanding that Q is equal to K at equilibrium. That's when our concentration of reactants and products is no longer changing because they are at the equilibrium point. So, if we have a Q value that is smaller than our K value, that means that we have taken our smaller number and divided it by a larger number, meaning our products, we have a smaller amount of products than we have reactants. We've got a larger value for our reactants, which means we've got a larger amount of reactants. That will give us a small Q value, relatively speaking. And if that Q value is smaller than our K value, that means that we are not yet at equilibrium. We've got more products than we've got reactants at equilibrium. And we say that the reaction proceeds to the right. So all of this again is with respect to equilibrium being in the center. We're proceeding to the right towards equilibrium. Conversely, if we have a Q value that is larger than our K value, that means that we have a relatively large amount of products to reactants. We have a larger number in our numerator and a smaller number in our denominator. And that means we get a larger Q value. We've got more products and reactants. We will see more of the reverse reaction. And we say that the reaction will then proceed to the left. So, small Q value means more reactants than products. Reaction proceeds to the right. When we have a larger Q value, that means we have a large amount of products. We'll see the reverse reaction, and the reaction proceeds to the left. So again, remember that that Q value is relative to our K value. We might think that with our perspective that we see a relatively large or a relatively small Q value just because that's what the numbers show. But that Q value is only relevant when we compare it to the K value and whether or not it is smaller or larger than the K value, because the K value is the ratio of products to reactants at equilibrium. Let's take a look at what this looks like in practice. So this is practice problem 17.35. At 425 degrees Celsius, our equilibrium constant, is 4.18 times 10 to the negative 9th. For the reaction, 2 HBr gas yields H2 gas plus Br2 gas. In one experiment, 0.20 atmospheres of HBr gas, 0.010 atmospheres of H2 gas, and 0.010 atmospheres of Br2 gas are introduced into a container. Is the reaction at equilibrium? If not, in which direction will it proceed? So, we're dealing with partial pressures here, which is nothing scary, simply a thing to note. So, when we are writing our reaction quotient in partial pressures, it will look like this. We've got our partial pressures of our products times our partial pressure of our other product divided by our partial pressure squared of our reactants. So all we need to do now is plug in some numbers and then compare our K and our Q values. So we have 0.010 times 0.010 and 0.20 squared. When we simplify that out, we see 0.0001 divided by 0.04. And when we simplify that one step further, we end up with 2.5 times 10 to the negative third. So we now have our reaction quotient at this particular moment, so at the initial outset of the reaction. And we need to compare our Q to our K. So we've got 2.5 times 10 to the negative third is our Q, our reaction quotient, and K is 4.18 times 10 to the negative 9th. So we can clearly see that our reaction quotient is significantly larger than our equilibrium constant. When QP is larger than KP, so when our reaction quotient is larger than our equilibrium constant, what direction will the reaction proceed? It will go to the left. So remember, in this instance, this indicates that we have more products than at the current moment than we will have at equilibrium. So we need to see some of the reverse reaction to convert those products that we have currently and turn them into our initial reactants. And there you have it.